This is project number 2, video number 1, the pencil and paper part. First thing I want to note is there's a fifth argument, namely the position of the moving particle at time 0, how far away it is from the fixed particle. Okay, our idea is we got two charged particles, one fixed, the other one is initially moving away from it. They have opposite signs, so the force on the moving one is attractive, and so it's going to be slowing down, eventually come to have 0 velocity and then start heading back, and they want to know how far away that moving particle gets from the fixed particle and how long it takes to get there. Now the first part is going to be straightforward. That's just conservation of energy. E is equal to E prime, solve for that distance. The second part is going to be tricky because conservation of energy, the principle that we're told to use in solving for this, relates position and velocity. So we're going to have to use position and velocity information to get the time that is being solved here. So let's get to work on the easy part, that first part. I got two charged particles of opposite sign. I'm going to make the fixed one a negatively charged particle. Actually, you can make it either by assigning the value to Q1, but I'm going to picture it initially at least as being a negatively charged particle. Then the moving one has a velocity I'll call just V0. You could call it V20 if you wanted to, because it's the velocity of particle number 2. I think I'm going to go A and B. I'm going to use the numbers for other things. And then I'm going to have before, I'm actually going to have an intermediate in the before picture, by the way, they're at a distance R0 apart. Here in the intermediate picture, I'm going to have them be a distance, this is A and B again. This one's got a mass, MB. There'll be a distance R apart. And this one will be moving with velocity V. And then in the final picture, I got them at their greatest distance. I go V F equals 0, and that they're at a distance RF. So that's at that instant when particle B has achieved 0 velocity. So first off, I said let's go ahead and find out what RF is. I'll go E0 is equal to EF. So kinetic energy in the initial picture plus the potential energy in the initial picture is equal to the kinetic energy in the final picture plus the potential energy in the final picture. This will be 1/2 mv0 squared plus q times phi 0. Now phi 0, that's QB. Phi 0 is the electric potential at point B, which is where, well, at this location in space, where charged particle is at time 0, charged particle B is at time 0. But imagine that not being there. What the potential due to A at that empty point in space is, and then now we can put QB there, so we'll get the potential energy. So phi 0 is the electric potential at this point in space where B is, due to charged particle A. In the after picture, the particle B is not moving. VF is equal to 0, so I'll just set that equal to 0. I think I'll try to do that a little bit more neatly, maybe in a different color. So this KF is 0, and UF is the charge of B times the potential energy that A creates at that location. So I'm going to call that phi sub F. So that's 1/2 mv0 squared plus QB times KQA over R0 equals QB times KQB over RF. And one of the things the program is supposed to find is the RF, so I want to go ahead and solve that for RF. I think I'll multiply both sides by RF and divide both sides by everything that's on this side. Also, I'm going to distribute this QB. This was QA, the electric potential, KQA over RF. That's the electric potential due to charged particle A at a distance RF from particle A. So RF, now I'm going to distribute that QB is equal to K QA QB. That's what's left on the right side after I multiply it by RF. And then on the left, all I'm going to have is that because I'm going to divide by all this stuff. 1/2 VO squared plus K Q, oops, Q, not G. QA QB over R0. I've just distributed that B a little bit. And, okay, which is equal to, let's see, I think I want to divide top and bottom by K QA QB, so it'll just be a little bit easier to evaluate, I think. So I have MVO squared divided by 2. That's what I started with, the 1/2 MVO squared, and then I'm dividing every term on the bottom by QA KQA QB QA QB, and so I have plus 1 over R0 here. So this term obviously has dimensions of 1 over distance. This is energy, and this is energy per, well, energy times distance. Because if I had an over R there, it would be an energy. So that makes this just 1 over distance, just like that one. 2 times 1, adding the two 1 over distances, I get 1 over distance, and the reciprocal of that is distance, which is what I want. I want a distance. Okay, so the units seem to work out there. And that's more or less my answer for the first part. RF equals this expression. I'll call this equation 1. Alright. Now comes what to me is the tricky part. What I'm going to do is create an array of R values that go, here's my QA. This is this is R0, where R0 is actually the distance that this point is away from there. And then there'll be another one that's a distance R1 from there, and one that's a distance R2. And then all a whole bunch of them up to Rn, where the nth one is equal to Rf, the maximum distance that I get away from it. And then at each one I want to calculate the velocity. Find the velocity at an intermediate point. Find v at intermediate distance. In other words, not just all the way out there, so I guess these are all represent intermediate distances. All these are intermediate distances. I'm going to write a formula that's good for them, but I think it'll also give me the first one, and the last one. Let's see. To do that, I'm going to be referring to the before and the intermediate picture. So I'm going to use subscript 0 for the before and no subscript for the after. So I'm going to use that as the before and after diagram for E0 is equal to E to get the velocities. So that's K initial plus U initial is K intermediate plus U intermediate. That's 1/2 mv0 squared plus q phi 0 is equal to 1/2 mv squared plus q phi. That's 1/2 mv0 squared plus, well, this was qb, and the phi is the electric potential at the location of charged particle B due to charged particle A. So that'll be qb k qa over r0 equals 1/2 m times the square of the velocity at the intermediate position. This is all mb, by the way. We only have one mass in the problem, so maybe I can get away with calling it just m. That's what I've been calling it up here so far. So I'm going to use the symbol just m to represent the mass of particle B. So it's got a charge q sub B and a mass m. Alright, let's see if we can move on from there. I think I've used the symbol m throughout except for at the very start, and I almost switched there at the very end. Okay, plus the charge of particle B times the electric potential at the location of B due to charged particle A. So QA divided by R, the intermediate distance. So my plan is I've got the initial distance, and I've got, that's where it starts, and I've got the final distance at this point. And so I'm going to create an array of values from that distance out to that distance. So I have n values out to there, and this formula would be good for any one of them. So this, if I'm talking about the fifth distance, this r will be that fifth distance. So you can think of it as a variable. And we're solving for the velocity. I want to get the velocity at all those positions. So the velocity is a function of how far out I am. So I think I'm going to subtract this from both sides, put it on the other side, multiply both sides by 2 over m. So that would give me v squared over here, and then I'm going to have to take the square root of both sides in order to do that. So here I have 1/2 mvo squared plus this term minus that term. They both have kqa, qb in it, so I'll factor that out. And I think I want to make this into a square bracket then. K, QA, QB times 1 over R0 minus 1 over R. And I think that's the end of that bracket. Alright, so I subtracted this from both sides, factored out the KQ over A, and I have this plus that this term minus that term with the KQ over A factored out. That's 1 over R0 minus 1 over R. Okay, that looks good. That's all energy, and 1/2 mv squared is an energy, by the way. And divide that by mass, and I'm going to have units of velocity squared in both terms. Take the square root of that, I got units of velocity. The units work out. It looks pretty good. I think I'll go ahead and distribute that 2 over m. And so I have v0 squared plus 2kqa qb all over m times 1 over R0 minus 1 over R. Alright, that gives me a formula for the velocities. I'm going to call that equation number 2 for the intermediate velocities. And I think that's all I need for my equations. Now I can start. I think I'm going to, in step 1, start my outline of the program. I'm going to start with a function definition, and I'm going to have 2 return variables, RF and T equals my function name. You make up your own function name, please, but I'm going to call it get distance and time. And it's got 5 arguments. Fixed charge, charge of the moving, mass, speed, and then that distance, which I forgot to put in the initial version of it. So QA, QB, mass, it's the mass of particle B, V0, initial velocity of particle B, and R0, the initial separation of the 2 charged particles. In other words, how far the moving one is from the first one. So now I've got to create an array of R values. I'll call it R array equals linspace of R0 up to RF n values. This is to be determined by trial and error. Get a value for that by trial and error. So I might start with 100, for instance. I might actually start out with 10, but then jack it up. I think 100 might work, but you know, if that doesn't work, I can try doubling it or multiplying by a factor of 10. N determine trial and error. Alright. Now, this represents n different points in space. Well, actually, it's going to be n minus 1 points in space. I think I'll call it n plus. It's n plus 1 points in space. No, it's n points in space, but it includes the endpoints. Okay, n points in space from r0, the initial distance that the moving charge particle is from the fixed charge particle, to rf, the distance it is from the fixed charge particle when the moving charge particle is at rest. Now, to find the velocity at each of those points, use v array equals, I'm going to call it equation 2 with r equals r array. So now, equation 2 was the one that gave me the velocity at any given point. I put r array in here, and it's actually going to create n values of v, one value at each value, for each value that we have stored in R array. And that'll be good. Then I think I want to get back up here to this picture. So I'm going to have like the initial velocity. Probably should have called that R1. I think I'll start with R1. But this R1, by the way, is equal to my initial distance, which is R0. So these 1, 2, etc. just represent the element of the array. I got n values in it. The first one is equal to R0. The one says it's the first one. The second one is R0, really plus RF minus R1 divided by n, since I got n of them and they're equally spaced, etc. The spacing between them, I think I'm going to want that. So I'm just going to call and for delta R is equal to R2 minus R1. Could have picked, R5 minus R4. The spacing between any two adjacents, the spacing between all of them is the same. So I'll just take the space between the first two. And then when I did that velocity thing, so I got delta R. This is delta R from here to here. And this is, I've also got the velocity at each of these. Oops, that's V2, V3, V4, etc., all the way out to Vn, which is should be 0. There could be a small issue, like if this is just off by a hair in the wrong direction. First off, this 1 over R0 minus 1 over R. R is getting bigger and bigger, so this is positive. So, oh, and this is a negative. One of these charges is negative. So this whole thing is going to be negative because, for instance, the way I drew it, QA is negative. QA is less than 0, but 1 is positive, 1 is negative. So this whole thing is going to be negative. So I'm subtracting off stuff from V0 squared. And so I got V0 squared minus something, and that something gets bigger and bigger until it's exactly the same size as V0 squared. Well, if there's a slight round off error, this could turn out to be a negative value under the square root, maybe very, very tiny, but still a little bit negative, and then I get an error. So if I have to, I might do, I think I'll actually do that just to be careful. V array is equal to equation 2 with R is equal to R array of I think I'll do this from 1 to n minus 1, and this from 1 to n minus 1. So all but the last element, and then I'll say v array. Gotta get that delta r a little bit later, but v array of, it's really that stuff goes in parentheses, but that doesn't really, I don't really have to get that right here. This is just the idea of it. The v array of n is 0. So the last position is 0. It should work out to be 0 even if I didn't like calculate explicitly all but the last one. But if there's a slight round off error, I'll get a negative square root, and then I'll get an error even though it's just, you know, it's really 0, but it's off by a hair and making that part under the square root negative. So just avoiding a possible pitfall there. Then I said something, oh yeah, delta r is r2 minus r1. Not really being consistent there. That should be r of 2 minus r of, the 1 in parentheses, but it's alright. Just the idea here. When we program it up, we have to get the syntax right. And then this is going to be it. I'm going to say the time for it to get from one position to another, say from R3 to R4. So from one position to the next, I should say. From distance of speed times time, the time will be the distance divided by the speed. And what I'm going to do is use the average speed in here. So I'm treating it as if it's got a constant speed from here to here, and that would be very bad if that was a large distance, but I'm going to choose n big enough so that the speed changes so little in there that it's okay to treat it as a constant. And it's probably, I could use the beginning value or the end value. I'm going to choose to use the average value in between. So my idea is the time to get from position 3, from R3 up to R4, is the distance between them, delta r, divided by the average speed that it has when it goes from there to there. And it's not really quite the right average speed averaged over time, but it's going to be the speed 3 plus the speed 4 divided by 2. So an approximation to the average speed, I'll call it. So I'm going to go T array and this is going to be from 1. I'm going to go T array of 0 is equal to 0. Well, of 1. The first one is just equal to 0. And then, the time that it gets from the takes to get from the initial position to the initial position is 0. It's kind of a tautology. And then T array for the rest of them. This is collectively for element 2 up through element n. Is going to be delta r divided by, and I'm going to have an array of average values of velocity. So v array of 1 up to n minus 1 plus v array of 2 to n, all divided by 2. So in other words, the first element that I put over here is going to be T array of 2. what it's going to get in it is the distance between any two adjacent particles divided by, and then the very first one, it's going to do it for every element in the array, but the first element is going to be the array, the first element of the array and the second element added together divided by 2. Then for the next one that I put in here, where this will be 3, this will go delta r will be the next one, and here where this goes from 2, and that's a 3, so it'll be the third value of the velocity. The second value of the velocity plus the third value of the velocity, all divided by 2. So that should give me the rest of the array at time values. So now I've got n values in the time array. The first one is 0. It's just for completeness. I didn't really need to bother with it. 0, but I felt like it. And then the t is going to be the sum of all the elements in the t array. Like each element is the time that it took to go from one point to the next. The total time to go from the initial point to the final point is just going to be the sum of all those times. And that is, I think that does it for the pencil and paper part. Let's just make sure that use conservation of energy. We use that to determine and return a single one-dimensional array of 2 values, namely max distance in meters. That's the RF and the time. So back over here, my 2 returned variables are RF and T. I assign the T in the last step here and the RF. I seem to have forgotten, so I think I'll put step 1.5. I've been using it. Like I used RF right here, so I'll call this step 1.5. Use equation 1 to get RF. So I guess I thought I had done that. Yeah, there's equation 1. RF is equal to, and this is all given stuff. The mass of particle B, the initial velocity of particle B. K is a known constant, so I have to actually in the program tell it. I'll call that step 0. Say K equals 8.99 times 10 to the 9th, which would be E9. So this is for the computer E9. If we were writing it for humans, that would be times 10 to the 9 x1 0, and then the 9 would appear as a superscript. That 9 doesn't look much like a 9. I'm actually going to be using this outline, so I got to write it so at least I can read it. E to the just E9 is enough. That implies times 10 to the 9. Okay. So now I got the RF that it said to get, and I have assigned the T value, and probably a good thing I checked to see if I had everything. And let's look down here for complete algebraic solution, including any relevant diagrams for each function. There's only going to be one function. I only need one function and an outline of the steps the program will execute. So I got my algebraic solution and I have my outline. In my algebraic solution I did indeed have some diagrams. I had turned out I was able to get by, well, I used 2 diagrams really, this before intermediate and final diagram, and then this diagram to tell you what I was going to be doing, and I had a whole bunch of points that were going to be occupied by particle B. This one has charge Q sub A, by the way. So I think I've got it. Let's call that a wrap on video 1 for project number 2.